Good day, everyone. We are Group 7 from ECE 3204, and we are honored to present our final project for ECE 411, Modulation and Cooling Techniques. Our project is entitled AquaShield, an IoT-based smart drainage monitoring and control system for flood prevention. I am joined today by my groupmates Pamela Medrano, Dashiell Cyril Moster, Gian Joy Ramos, Lee Mark Tabing, and myself, Gabriel Luis Martel. Today, we will show you how AquaShield uses real-time monitoring, smart sensors, and automated control to provide a more efficient and reliable solution for flood prevention and drainage management.
Flooding remains one of the most common problems in urban communities. While heavy rainfall is often blamed, flooding is also caused by clogged drainage systems that prevent water from flowing properly. When debris blocks the drainage, water quickly accumulates and causes localized flooding even during moderate rain. The traditional drainage monitoring still relies heavily on manual observation, where authorities only respond after flooding has already started. This delay can lead to greater damage and safety risks. Because of this problem, we introduced AquaShield, an IoT-based system capable of automatically monitoring water conditions, detecting drainage blockages, and activating protective mechanisms in real time.
To guide the development of our project, we established four main objectives. First, to design a smart drainage monitoring and control system integrated with sensors, an automated flood barrier, and a real-time IoT dashboard. Second, to develop a microcontroller-based system that can process sensor data, classify drainage conditions, and support both automatic and manual operations. Third, to test the system under different scenarios such as normal flow, warning levels, blockage situations, and danger level flooding. Finally, to evaluate the system's performance in terms of accuracy, response time, and consistency of outputs.
For the system design, the core component of AquaShield is the SP32 microcontroller, chosen because of its built-in Wi-Fi capability, which allows communication with the IoT dashboard. The system uses multiple sensors, including an ultrasonic sensor for monitoring water level, a rain sensor for detecting rainfall intensity, and a flow sensor for measuring water movement inside the drainage. To automate the physical barrier, we integrated an L298N motor driver and a DC motor. Through this setup, users can remotely monitor the drainage condition while also having the option to manually control the barrier whenever necessary.
For data processing and visualization, the dashboard displays all sensor readings in real time. On the water level monitoring interface, users can observe water depth, flow rate, and gate status. Meanwhile, the rainfall timeline records rainfall intensity over time and categorizes it into light, medium, or heavy rainfall conditions. By combining rainfall data with water flow information, the ESP32 can determine whether flooding is caused by strong rain or by a blockage inside the drainage system. This improves the reliability and accuracy of the alerts generated by the system.
The flowchart of AquaShield demonstrates the intelligence of the system. Once powered on, the ESP32 connects to Wi-Fi and continuously reads sensor data. If the condition is normal, the barrier remains lowered, and when the water level reaches a warning threshold, alerts are triggered. And if rainfall is detected but there is little or no water flow, the system recognizes this as a blockage condition and immediately notifies the user to inspect the drainage for debris. In danger conditions, the system automatically raises the barrier to prevent overflow and flooding. A manual override feature is also included, allowing users to directly control the system through the dashboard.
To validate the effectiveness of AquaShield, we conducted several scenario tests. The first one is under the normal conditions. In here, the green LED indicated that the system was operating safely. The next one is during warning level conditions. The yellow LED signaled caution. So for blockage testing, we simulated rising water with minimal flow, and the system immediately activated the red LED and the buzzer to warn people. Finally, during danger level testing, The system successfully activated the red LED, buzzer, and the automatic barrier mechanism to prevent the water overflow. This results demonstrates that reliability and responsiveness of the system in different environmental situations.
For performance evaluation, we tested the system under varying rainfall intensities. Even during no-rain conditions, the system was still able to classify warning states based solely on water level readings. During light, medium, and heavy rainfall simulations, AquaShield consistently detected blocking situations whenever the measured water flow did not match the expected rainfall intensity. For example, during heavy rainfall, if the drainage flow remained stagnant, the system maintained a red alert status. This proves that AquaShield does not simply react to rising water levels, but intelligently analyze the relationship between rainfall and water movement to provide accurate, real-time monitoring and alerts.
To summarize our methodology, AquaShield follows a four-stage process: acquisition, processing, classification, and response. First, the sensors gather raw environmental data. Second, the SP32 processes and analyzes the sensor inputs. Third, the system classifies the condition as normal, warning, blockage, or danger. Lastly, the system responds by activating LEDs, the buzzer, or the automated flood barrier. This closed-loop process allows the system to provide continuous monitoring and protection without requiring constant human supervision.
This circuit diagram presents the physical architecture of AquaShield. The sensor positioned throughout the system serve as the primary data gathering components. One important feature of the design is the boost converter, which supplies stable voltage to the ultrasonic sensor. The ultrasonic sensor is responsible for detecting the water level by measuring the distance between the sensor and the water surface. Since the sensor requires sufficient and stable voltage for accurate distance measurement, the boost converter ensures reliable operation, and the measured data is then used by the system to monitor flood conditions and trigger automated responses when necessary.
In conclusion, AquaShield provides a comprehensive IoT-based solution for flood prevention and smart drainage management. By integrating sensors, automation, and real-time monitoring through the ESP32 platform, the system transforms traditional flood monitoring into an active and intelligent response system. Based on our testing results, AquaShield achieved accurate and consistent performance across all scenarios. The dashboard alerts, sensor readings, and barrier movements match the expected outcomes during testing. Through this project, we successfully achieve all our objectives and develop a scalable, reliable, and effective flood prevention system. That's all, and thank you for listening. We are now ready for your questions.